Thank you, Aaron. So this talk is about making things, and we're going to go into a subject that I've been thinking about for 3 years now, which is WebAssembly and IoT. But a brief about me, product manager, work on all sorts of developer stuff. I organize the WebAssembly SF. So if you're in town in the Bay Area, please come on by. If you happen to be in town while traveling, you're always welcome. I'm currently taking some time off to work on open source and IoT. And if you're into that sort of thing, come find me, either at the event, and if you're watching the recording, I'm on Twitter as Beri Kicks. It's a long, boring story around my Twitter handle. But show of hands, does anyone know what an Arduino is? Okay, so everyone in the room basically. But if you don't, it is a very tiny computer. It's the type of computer that you might put into other things, that you can write software on it, you can control it, and control the world around it. Turn LEDs on or off, start, stop motors. We call those microcontrollers. And whenever I bring up WebAssembly and IoT, the first thing people ask me is, can you use WebAssembly on an Arduino? Is such a thing even possible? Hopefully, we'll answer that today, and a few more things. So here's the very brief agenda of my talk. We're going to define that term IoT in short detail. Why would you even want to run WebAssembly on Internet of Things devices? And lastly, the current state of WebAssembly and IoT with some demos that are being previewed here briefly, and sort of the future, where I think it can go, and some opportunities for us to collaborate on making it even better to use WebAssembly and IoT. Cool. Let's start with the definition. IoT, I'll use that term interchangeably, but as many of us know, that's short for Internet of Things. And, well, we have a lot of things in our life that have internets, right? Smartphones, laptops, servers. And when we talk about Internet of Things, we actually don't mean these things. Instead, we talk about those things. Bluetooth headphones, speakers with built-in assistants in it, connected door locks, self-driving cars, washing machines, on and on and on. And these are actually a different class of devices. We often call these embedded systems, which I'll explain a little bit more, but they're fundamentally different than our smartphones and our laptops. And one of the key differences between a smartphone and a Bluetooth headset is that they are constrained devices. So we call them embedded partially because the entire subsystem is inside the product, and it can't be upgraded, it can't be scaled up or scaled down. And every aspect of that device is sort of constrained. And what we mean by constrained is a couple axes. For one, processing power. Memory, storage. If it's a battery-powered device, you're constrained on how much juice you can draw. And other things like the connectivity. If it's a cellular device, how much bandwidth you can get, and so on. And these constraints are driven by cost. If you're building a consumer product, even shaving off 1 penny would be a significant savings in the long term. So while you could put a laptop processor in a Bluetooth headphone, that's probably not the most cost-efficient choice, and probably require really big batteries. But sort of a frame of reference. Why we use this constrained term is, let's take that Bluetooth headset. They'll probably have a processor on it with 64 megahertz of processing power, single core. Maybe 120 kilobytes of RAM for the entire application. That's the underlying framework that's controlling the devices, that's the Bluetooth stack, that's the application that knows how to respond to the volume up and down. Not a whole lot of space. Maybe half a mega flash if you're not doing firmware updates. On battery-powered devices, let's say, I don't see any in this room, but a motion sensor that has a battery in it, it may need to run 2 years on a single AA. So it has to be very thoughtful of how it uses that power. And those scooters you see around the Bay Area with cell phone modems in them, they're sending their GPS signals back so you know where they are. Those might have 50 kilobits per second of upload speed. So very different than this Wi-Fi laptop or a server connected to Ethernet. And so that fundamentally changes how you design applications, because we have to live in a constrained world. And to program in this constrained world, we need special software. Right? We need software optimized for embedded systems. And we just can't be wasteful with memory and allocation and how often we turn and off hardware how often we dial back home. So there's a very rich ecosystem of software and frameworks that may be new to a lot of you, but have decades of development. Everything from open source that are running in robotics to things they put in rockets, and open source contributions abound. And they just basically encapsulate a lot of the best practices that we've developed in the embedded software world in a framework that you would expect in any other software discipline. And we'd be remiss if we didn't mention the internet part. I kind of glanced over in the beginning. But for these embedded systems, well, they typically have embedded radios in them, modems, radios. So things like Wi-Fi, Ethernet, but other forms of connectivity like Bluetooth and Zigbee, they're specialized because partially the cost that we have to get with battery or form factor. And so in embedded systems with Internet of Things devices, the internet connectivity is actually built typically inside the chip itself. And so once again, we have a constrained environment. That networking stack, the entire IP, if it's using IP, is not only constrained just like the rest of it, so it has custom IP infrastructure, but it might even be very hard to update. So it's burned into ROM. And it probably goes without saying, you can't just take a vanilla node and run it on one of these embedded systems because of the end-to-end constraints. Cool, so that is a summary of what we mean by Internet of Things. And we'll use that definition. That definition has changed depending on who you're talking to. But that's our baseline. So with that shared context, let's talk about IoT and WebAssembly. Kind of a strange concept if you are not from the future and already seen my talk. For me, it all started in 2017, like many of us, seeing one of Lynn Clark's code cartoons talking about WebAssembly, or what maybe it was one of her talks, and in the use cases section, there was a bunch of things that weren't the web browser. Blockchain, tools, and Internet of Things came up over and over again. And if you just learned about WebAssembly in 2017 like I did, that might be peculiar. How do you even get there? It turns out that the creators of WebAssembly thought about contexts where WebAssembly might be used outside the browser from the beginning. And if you read the spec, there's a section about embedding, and the explainer site, webassembly.org, it goes into more detail about non-web embedding. And that's really it's in the context of, this was developed originally for web applications, but all these different use cases where a portable, safe, secure, low-level language and runtime could be used makes sense in a whole other applications. We just spent 10 minutes talking about what is a constrained environment embedded. That's kind of like the web browser if you squint at it. You have to manage memory. You have to be careful with users' battery. You want to save their data. So the solutions that are brought forth by WebAssembly just make a ton of sense. And so where's my interest in WebAssembly and IoT? In 2017, I was working for a startup called Particle. They're a hardware and software company to help you build internet-connected things. And I worked on the embedded system platform. I was the product manager, obsessed with how developers use our hardware integrated into their products, how they program that device with our flavor of an embedded operating system, and all the developer tools that they would use to actually get their code onto the device. So I thought a lot about developer experience, and I talked to a lot of our developers about programming embedded systems in 2017. And, they wrote C++ code because that's the way you write C++ embedded applications, primarily still to this day. But we also had a lot of developers who weren't super proficient in C++ code, and they asked for something different. Well, we got bitten by the Atwood's law. Does everyone know Jeff Atwood's and Atwood's law? So he created his own law, which is also awesome to do, that states any application that can be written in JavaScript will eventually be written in JavaScript. And he actually has spoken many times about this law after he wrote it. That's not simply about JavaScript, the programming language. It's about high-level abstractions. And as a platform gets more mature, there are people who are comfortable in high level, and there are people who are comfortable in low level. And they're both contributing members, kind of like what Ashley was talking about earlier. And so the question I got maybe once a week on our forums was, can I run JavaScript on Particle? And that seemed like a hard problem, because we didn't have a lot of RAM. V8 takes more than 128 kilobytes, as we know. But it turns out there are a lot of communities who are also interested in improving the developer experience of programming embedded systems. In fact, there's a whole micro ecosystem of embedded runtimes targeting specific languages. There's ones for JavaScript. The Rust community actually has its own working group focusing on this problem. There's CircuitPython for Python, Lua. And we started to look into these. Turns out there's a lot of implementations of JavaScript. Seems to be pretty popular. But as we, building platforms, had to look at, well, which one do we pick? Because to build duct tape into our framework would require a very specific implementation for the duct tape runtime, or the JavaScript runtime, or the Arduino runtime, and so on and so forth. So we couldn't scale out our implementation because of the nature of programming these constrained embedded systems. So either we had to pick one or build some sort of shim that the community could use that seemed to be crufty and hard to maintain, which brought me back to why I got interested in WebAssembly. Said, well, the folks who are designing this thing talk about how you can have multiple programming languages come together. It can open up to new ways to build applications on the web and beyond. That sounds like the thing I want to solve for developers building on hardware. And basically, we were proposing, well, use WebAssembly as the intermediary language for programming these devices. We, as the platform provider, can take our C++ code, compile it into WebAssembly. Through some sort of module system, which I didn't know how to do, we could expose that as a programming interface to the different runtime maintainers, like JavaScript from the JavaScript Foundation. And they can compile their runtime into JavaScript, and all we have to do is a little bit of shim, and now developers can have their choice of languages to work in this environment. But it was still 2017, and there wasn't an embedded runtime that we could use for running that WebAssembly code. This is a great GitHub, by the way. It's the awesome WebAssembly runtimes. It's a collection of every known WebAssembly runtime, both in the browser, on the server, and spoiler, on embedded devices. But there was nothing there. The closest there was something you could run on effectively a Raspberry Pi, and it was hard at that. So I kind of gave up, and we moved on. But now we're in the future. It's not quite 2017, and it's a really exciting time for this idea of running WebAssembly outside the browser. Now, I'm going to talk about 3 different areas. Some of them are here now, and a lot of it is what I would like to see us move towards the future. And maybe ideas for projects if you guys want to work on open source and IoT. It's sort of these 3 different areas and their status. The runtimes themselves, the thing they were missing at Particle, protocols and IoT protocols. We'll talk about what those are. And the tooling around it. As you can see, this is basically what I was trying to do in 2017 as a snapshot. So 2017, 2018, most of the development was happening in the web browsers, and we started to see some server-side applications and frameworks for building WebAssembly into the cloud. But it wasn't until mid-2019 that we even saw folks trying it. And the very first implementation was from the Intel team, and they have the Wasm micro runtime, or WEMR. It is exactly what I was looking for. It is a runtime that can run on tiny little devices like this one right here on the stage. If you can't see it on the camera, I'll show it later. It allows you to take WebAssembly binaries and compile it into your final application and deploy it onto devices. They're even experimenting as early as 2019 with creating an application framework so you can deploy subsets of binaries to your application so you can get that app-like experience on an embedded system. And they were bleeding edge. It was mostly research, but then they released the working version on GitHub. And you can see on my left, your right, maybe a $5 development board with a touchscreen showing a demo of a UI where you're tapping the button and it's rendering a full interactive UI. And on the right is the entire framework of what's enabling that. And so, I mean, I kind of feel vindicated because we now have an embedded runtime. It is exactly fits that first use case. And what's cool about Whammer, I didn't mention it earlier, but they contributed that project to form the Bytecode Alliance with other folks who are trying to push WebAssembly beyond the browser, and it's a great foundation. You can take it, run it on a device, and build a blinky light like what's happening here. But I'm also, besides a WebAssembly nerd, an operating system nerd, and one of the other areas that I'm really into is unikernels. Has anyone heard of unikernels or microkernels and that sort of spectrum of alternative operating systems? So in a traditional operating system, I'm going to get to the segue, don't worry. In a traditional operating system, you have general purpose software. Maybe if you're running a web server in the cloud, you have all this stuff that comes along with just, let's say, your web server, including floppy drivers, by the way. And that's a bloated operating system, takes up memory, takes time to boot up. But for mostly in academic realm for the last couple decades, people are saying, well, what if we only brought the parts of the operating system we need, package that up as an application-specific operating system, and we can get a lot of nice benefits. That's where the uni kernel comes from. It's a one-time use application kernel. The nice thing about that is it can load faster. So things like serverless functions are really interesting. It is smaller, so you can fit more applications in the same server. And there's other things like smaller attack surface area. There was an exploit a couple years ago because some of the most common VMs on AWS had floppy drivers, and there's a way to use floppy drivers to get root access, which is terrible. In a unikernel, you strip all that unnecessary bits out of it. So it sounds similar to the specialized operating systems for embedded systems. In fact, they share a lot of lineage. So if you squint, a unikernel is kind of like an RTOS, or an embedded operating system, but for different types of devices, more like servers. And probably the most interesting projects going on right now is from the Linux Foundation. It's called Unicraft. It's a framework and a series of libraries and a tool chain to build unikernels. Because before it was mostly academic. Here they're trying to open up to whole other use cases, whether that's VMs on the server to fit as many node applications as you possibly can, to containerize orchestration, and even bare metal. So bare metal, we think of bare metal servers. Their use cases also in automotive applications, running it on cars, which is cool. But I saw bare metal and I thought, hey, this could be another use case that is similar to IoT devices. So I reached out to the folks at NEC Labs, who's doing the main development, and they ported Whammer to a unikernel. So I'm super excited. This is probably the first time it's being shown. Also, they just pushed this code either yesterday morning our time or today. I don't know. This code is available, and I have some hardware here. But let me try to walk you through lock screen of doom. You can plan for demos, and then the lock screen. I will try to maximize this, and I might loop it around and explain you what's going on. So what you can't see here is, well, that's a screen, a very small screen. Actually, it's this size. And there's a Raspberry Pi behind, and it's off. And when they enable the power, oops. One more. Promise you guys will see this demo eventually. So when they turn on the power, it's booting up for the first time, and now the application is loaded, and he's touching the screen, touching a button. So there's a lot of interesting things that are happening under the covers that aren't obvious in this demo. I'm going to walk you through it. One, it's a good screenshot, a little blurry, is the boot time. So if you see on the screen, that says 1900 microseconds. That's 0.01 10 milliseconds. So this application booted from off to on in 10 milliseconds. And if you know anything about servers, or actually take a Raspberry Pi, that can take 20 to 30 seconds from a cold start. If you're building a mission-critical application and it goes offline real quick and it turns on, somebody's having a bad time. If you're building a server and you're trying to do a serverless function, going from 100 milliseconds to 10 milliseconds is already big savings. Going from 30 seconds down to 10 seconds is huge. So this is a really fast implementation. It's also booting up WebAssembly via Whammer in that same time. So when you see the screen the unikernel is already booted, Unicraft's already booted, the WebAssembly runtime is already hot, and the UI is already loaded. The code size is also very notable. It's 400 kilobytes. If you were to take the same application, build it in some other framework, it would be a lot bigger. If, for example, you're using something like V8 to render this as a UI, or just a web application, you're already talking about megs, if not more. Memory is also extremely low, 100K. And there's one peculiarity about this particular demo, which is to not take away from Unicraft. The Raspberry Pis are weird devices. I don't know if anybody's used a Raspberry Pi, but they actually load their firmware first from device into the GPU, and then from the GPU into the application. That's not typical in most embedded systems or MPUs, so that 2 seconds is just the Raspberry Pi's GPU warming up. In other devices, that's 0. So you literally can have a cold start operating system with a UI or a server or whatever in tens of milliseconds, which is pretty awesome. Quick summary, if this will let me, quick summary, maybe? We'll try to quick summary it this way. Yeah, so in summary for that demo, it was Unicraft running Whammer on a off-the-shelf Raspberry Pi, $35 development board, with a graphics stack, with threading, with an IP stack, which we didn't show in the demo, and a very small version of standard C library. And the neat thing about unikernels is it takes these as individual modules, packaged up in a single Raspberry Pi, you just flash it to your device, and as the Unicraft project adds more capabilities, you can bring more capabilities into unikernels itself, or expose it to Whammer. So if there's particular features of an operating system or a piece of hardware that you want to take advantage of, boom, now you have unikernels and WebAssembly. So, I mean, that's the coolest thing I've ever seen in the last 3 years related to WebAssembly, so I want to give them a round of applause. Just. And that would have been enough for me. We now have a progress. The Bytecode Alliance is moving forward and making this more ubiquitous and more useful. But kind of like an early New Year's present, there was another runtime that just popped in around October of last year. So within 6 months, we have 2 runtimes for embedded systems. It's called Wasm 3. It's from the folks behind Blink, which is an IoT platform. And they're obsessed with speed and performance. So they have a very specific type of interpreter for their WebAssembly runtime, but they designed it from the beginning to work anywhere. So it can run on Mac, it can run on Linux, it can run on bare metal, and it can run on embedded systems. And they have this one standard demo, which does Fibonacci sequence or something, which is cool. They also make it run on little IoT devices. So this is the ESP32, it's a low-cost development board. I've used it in finished products, so it's definitely production grade. And it has the little computer inside, the microcontroller. Here's one of these right in my hand, as well as the Wi-Fi on board. So it is a true IoT device by my own definition. And it's effectively a Wi-Fi Arduino. So you can program it in the same way you would do a normal Arduino, but you also have access to its internet stack. And I reached out to those folks. I like to reach out to folks and try to get demos out of them, which is really nice of them, and for this talk. And that's got the Fibonacci thing, and actually it's blinking some lights here. But of course, there's awesome people on the internet. Alvaro, who is a GD IoT expert, he took that demo and ran with it, because an internet thing device with internet hardware not talking to the internet is just plain silly. So he actually did all the hard work to get this particular demo up and going. And this is almost like the tour de force in demos, but let's see if I can get this one working better. So he just booted the device. You see a little hello from Rust. So he's running Rust directly on Wasm 3 on a ESP32. It's got an IP address because it has a full Wi-Fi stack. And he's going to reset it. And now it's running TinyGo, which is a Go for small places, as Lon talked about earlier. Same functional code base in a different language. For funsies, he's curling from the device, from his machine back to the device, and he can show full round trips. Upload a new version, another reset, and now we have assembly scripts running on this device. So truly multi-language platform for running on embedded devices. Is that the whole demo? Yeah, it's the whole demo. So yeah, Wasm 3. Oh, there's more demo. I didn't even see this half. But he built a little web application. So going back to that question I asked earlier, WebAssembly and Arduino, is it possible? Yes, it is. Yeah. So this is exciting to me. Pretty much like a 3-year journey trying to get WebAssembly working on IoT. And that's really the state of the art, which I think is pretty cool, and we're going to invest more in that in runtimes and making runtimes more accessible. But there's a bit of opportunities for the future, because there's the whole other part of the developer experience than just running your code. So I call this future work, hopefully partnering with folks. I talked about IoT protocols. And if you've never worked in the IoT space, there are a bunch of protocols for devices to talk to each other. It's not Wi-Fi. It's not the internet protocols. It's layers on top of it. These describe, for example, data and how the data should be formed from a sensor to a gateway, or a cloud backend to a mobile app. And they're very specific. If you've heard of some of these, MQTT is popular, CoAP is another one, and there's a bunch of them. And some would say there's too many protocols. But they are used in many different applications. But oftentimes, they're hard to integrate, primarily because they were built by embedded people to run on embedded devices, and they're almost always in C, which arguably is a highly portable target. But it means it's harder to use in other contexts. So for example, one of the most popular MQTT implementations is Mosquito, and that's written in really performant C. But if you wanted to use it in your Go backend, well, you got to jump through some hoops. People end up just rewriting it from scratch. Similarly, CoAP, another IoT protocol, the referenced implementation is also in highly portable, but highly not easy to use C. And honestly, these are complicated, very deep require context implementations that there are people doing it from scratch in Go and Python, but they're either not on the same level of feature parity or oftentimes have security holes. So one area of opportunity, I think, for WebAssembly and IoT is to take some of these reference implementations and just make them work in WebAssembly. Right? We have embedded runtimes where we can use it. We also are seeing people doing it on the server, so that could tie it end to end. But there's some tooling and sort of transformation that has to happen. A lot of this is in WASI land, which we haven't talked too much about today, but that would open this up a little bit further. And so the last thing I'll talk about is developer experience at large, just sort of the tooling around all this. This is a bullet list, but the last mile of being able to run your code and be able to, for example, talk to a server is your actual at your desk development loop. And so, for example, to program a device, the most common way, if it's using USB, is the standard protocol from the USB group called DFU, or Device Firmware Update. Everyone uses DFU util. It's a great application. It's written in C++. It has quirks across across operating systems, but anyone who's building a tooling, like Particle, we had a CLI, we had to wrap DFU util in Node.js, and then we had issues with rendering in Windows and everything. Wouldn't it be great if tools for programming devices were also written in WebAssembly so they can be used in more places? Debugging works very similar on physical devices as it does for running applications. We just have an extra layer. OpenOCD is one of those extra layers. Again, C++, huge ecosystem, but we can't integrate it, for example, in Visual Studio Code without jumping through a bunch of hoops. We did that twice. And lastly, testing. Testing is a broad topic. Renode is an awesome IoT simulation framework. It's actually written in Mono, which means maybe Blazor could be used to help take testing and make it run everywhere. So. Just as a teaser of where tooling can go, there's a really cool project. It's really hard to, it's actually fine over there. It's using a implementation of DFU util, that protocol for USB to program devices. Very small part of it was written in JavaScript directly. Then using WebUSB, this project can take a very specialized device, because it's not the full DFU, and program it over the web in Chrome with WebUSB. Super awesome. Now imagine that experience for every type of embedded system, which I think could be possible only with WebAssembly. And just kind of wrapping up here, huge thanks to the Whammer team for putting together sort of my dream of embedded systems and WebAssembly. The Unicraft folks, they were awesome putting this end-to-end demo. I'll have the demo for the reception later. You can come play with it, ask me more questions. They're actually speaking at the next WebAssembly SF, which is plugged tomorrow. Vladimir, almost. Got Harry Potter in the mind. For putting together Wasm M3, the demo, and Alvaro, who just took it all to 11. Here are some links. We can go check out Whammer, the Unicraft site. It's got a ton of information. They just cut the new release, Wasm 3, our little meetup, Wasm SF, and our Meetups YouTube channel. And with that, thanks.